have today only one seminar by Sarbajaya, who is a postdoctoral fellow in David Seneschal's group. And she will present us her work on frustrated quantum magnetism and quantum spin liquids. Just before we start, Sarbajaya, are you okay with questions during your talk, or would you prefer them after your talk?
No, it's fine if people ask questions during the talk, especially if the question is necessary for them to understand what comes later, or if they feel like they're stuck somewhere, so they can ask. It's fine.
All right, great. So if you have questions, just feel free to unmute yourself and ask your question. So go ahead, Sarbajaya, and thank you again for presenting today.
Okay. Over the last decade or so, there has been considerable discussion about these so-called topologically ordered phases of matter, which cannot be described within the Landau paradigm, and where you cannot classify phase transitions using local order parameters, but can describe them in terms of something called a non-local order. And a very prominent example of this has been a quantum spin liquid state, which is roughly speaking, it's a state without any spontaneous symmetry breaking down to t equal to 0. It has decaying spin correlations, no long range order whatsoever, and it has harbors fractional and post-particle excitations. These are often easily realizable in systems which are frustrated magnetic materials, where these are insulating systems with local magnetic moments, where you have strong exchange interactions, but they're competing in nature, because of which you don't get a unique ground state, but you get a large number of low energy configurations. And now there's been considerable theoretical and experimental work in the area of quantum spin liquids over the last few years. Theoretically, the initial approach was to look for wave functions which can describe such states. And then people went on to describe model Hamiltonians, which can have a quantum spin liquid state over certain parameter regimes. Experimentally, there's been a lot of discussion about possible material candidates for quantum spin liquids, and also of what are the probes which can give smoking gun signatures for such states. But a very important development in this area happened when the Kitaev model was formulated by Alexei Kitaev in 2006. So this is interesting because there is a very rare example of an exactly solvable quantum spin model in 2D, which has a spin liquid ground state. It is the spin half model defined on a hexagonal lattice. The kind of spin-spin interactions you have are essentially bond-directional in nature, meaning that when you consider any two neighboring sites, you have spin-spin correlations of this kind, which are Ising-like basically. Only one spin component is active. And the way this is solved exactly is by introducing 4 Majorana fermions corresponding to every spin. So these satisfy the usual Majorana anti-commutation relations, and the spins satisfy the usual spin algebra. But when you write down this Hamiltonian in terms of the Majorana fermions, then it seems initially like you have a quartic. You again have a quartic Hamiltonian, but actually you don't. And the reason is because you essentially have something which is a product of the link variables and 2 Majorana fermions. Now, these link variables, which are also like products of this kind, are actually, these are actually constants of motion. So they all commute with each other, and they commute with the Hamiltonian, and they square to 1. So essentially, in any configuration, you can replace these by their eigenvalues. And so that is what results essentially in a quadratic term in this new Majorana basis. So you can see that the original Hilbert space can be block diagonalized into sectors corresponding to different link variables, meaning that you can consider different sectors, each of which correspond to different configurations of linked variables in your system. So this model actually is interesting because it has, even in the original spin basis, it has a large number of constants of motion. Like you can think of the placket operators. So if you consider a hexagonal placket, then for that, if you look at the spin on every vertex and look at the outward component of the spin, and the product of all of these components gives you something called a flux or a placket operator. These operators actually also all commute with each other and with the Hamiltonian, and they square to 1. So you can think of basically a particular configuration of the system where you can associate a number plus or minus 1 with every hexagonal placket. And if a placket has a value of 1 corresponding to this operator, then that is said to be a flux-free placket. And if it has a value of minus 1, then it has a flux. So the entire Hilbert space can be separated into different flux sectors. There's actually redundancy here. So if you describe this Hamiltonian in terms of the Majorana basis, then what happens is that originally for n sites, you have a 2 to the power 2n size Hilbert space, but now in the Majorana basis, it becomes 2 to the power 4n. But this is actually an artificial enlargement, and this can also be understood in terms of the fact that if you consider different configuration of link variables, because the WPs are also product of these link variables, essentially a large number of configurations of link variables actually correspond to the same configuration of fluxes in the system. So essentially, you need to project states which are described in the states which are described in the new Majorana state into the physical subspace. And this is done by using something called a projection operator, which is defined by a property of the spins. Now the ground state of the system, it so happens the ground state of the system is actually a flux-free state. So it is a state in which the fluxes corresponding to every placket is +1. And so naturally now what happens is, because you're in this particular flux sector, now the system becomes effectively, so you have effectively a quadratic Hamiltonian in terms of the Majorana fermions. And because it's also translationally invariant, you can do a Fourier transformation and you can solve that quadratic Hamiltonian and you can find out the dispersion. And this dispersion, like this can be different depending on which parameter regime you're looking at. But for the isotropic case, this is a gapless, this gives you a gapless dispersion, a Dirac-like gapless dispersion. So essentially the system has gapless Majorana fermions in its ground state flux sector. And it is also known that the Kitaev model has spin-spin correlations which are exactly 0 beyond the nearest neighbor. So it is, these are ultra short ranged. So this is a system which has short range spin correlations and it has these fractionalized excitations, Majorana and flux excitations. So this is a system which has a spin liquid ground state. Now, if it was possible to realize such a state in an actual experimental system, then that would possibly give us the candidate for a spin liquid state. So this is something which has been extensively investigated experimentally as well. So now...
Sarbajaya, may I interrupt you just for a question?
Sure, yeah.
So this redundancy is something that you assume, sort of, right? I mean, you assume that the system can be characterized only by the flux. And you have this redundancy because of that. But if you didn't assume that,
I'm not assuming the redundancy. So in the physical state, you have a total of 2 to the power 2 in size Hilbert space. And if you replace each spin by 4 Majorana fermions, then it is effectively enlarged. But this is not, so this is not actually a physical change.
Okay, right. Okay.
Yeah, so you have.
So in materials, it would be there too, if such materials existed.
Yeah.
Okay. Okay, thanks.
So, okay, now we know that if you want to realize these anisotropic magnetic interactions in experimental systems, then where can we realize them? Now in Mott insulators, we know that the low energy degrees of freedom are spin degrees of freedom. And in case of the Hubbard model, the effective spin Hamiltonian is a Heisenberg Hamiltonian, which is completely isotropic. But it has been known for a while that if you have systems with strong spin-orbit coupling as well, then it's possible to realize effectively anisotropic magnetic interactions in general. So, but in particular, Jacqueline and Caroline showed that for certain systems, which are basically D5 spin-orbit coupled ions in an octahedral environment, and I'm going to talk more about these, it's actually possible to realize specifically the Kitaev-like bond-directional interactions that you have. And it's possible to design such interactions in these systems. And prominent examples of such systems are, like, which have already been discussed extensively, are sodium iridate, alpha-ruthenium trichloride, lithium iridate. More recently, there's been a debate on various new systems as well, like copper iridate, potassium iridate, and so on, but these are still under debate. The work we have done is in fact on one of these candidates, which is sodium iridate. Okay. Now in these systems, the effect of the spin-orbit coupling essentially is that you have spin-orbit coupled low energy degrees of freedom. So what this means is, let's take the particular example of sodium iridate. Okay, so in sodium iridate, you have a 5d5 electronic configuration. So these are 5d orbitals, which are initially degenerate. So now, because of the charge distribution you have around the iridium atoms, because each iridium atom in sodium iridate is surrounded by an oxygen octahedron like this. So because of that, there's a lifting of degeneracy between the d orbitals, and depending on the symmetry, you have a lifting. You have 2 sets of orbitals now, which are called the T2G and EG subspaces. Now you have 5 electrons in the T2G subspace. Okay, so this energy scale is pretty large. It's the crystal field splitting, which is of the order of 3 eV. Now the Hund splitting in the system is much smaller in comparison. It's 10 times smaller. So normally you would expect, due to the Hund's rules, that you would have spin parallel configuration corresponding to different orbitals. But here what happens is, because the scale is much smaller, you end up getting a pairing of spins, and you end up having, because of that, an effective low spin half configuration in the T2G subspace. So now in the T2G subspace, you can also do a sort of mapping between, so what is done is that you have a mapping between this L equal to 2 orbitals and effective L equal to 1 orbitals. And from addition of angular momenta, you find J effective equal to half kind of degrees of freedom in the system. So these are spin-orbit coupled degrees of freedom. This is generally true for all of these systems. Now it was also shown like a while back that the most general kind of magnetic Hamiltonian you can have in the presence for Mott insulators with strong spin-orbit coupling is of this kind. So you can have, first of all, a Heisenberg term, which is the anisotropic term. And then there's an anisotropic part. So the anisotropic part is, first of all, the DM interaction. And thirdly, there's something called a pseudo-dipolar tensor or a symmetric 3x3 tensor. The Kitaev term is actually a special case of this. So if you have only one component that is non-zero here, that would be your Kitaev term. Now, okay, so now the way you get the Kitaev interaction in these iridates or these kind of systems is actually a combination of this property of the strong spin-orbit coupling as well as the specific bonding geometries that you have. Because typically what happens is it is also known that to the lowest order, when you look at the effective spin Hamiltonian using a strong coupling expansion, you essentially do have a relation between these two. So because of the symmetries, you essentially to the lowest order actually, if you have a bond which has an inversion center, so this DM interaction vanishes, then this will also vanish. So to the lowest order, what you will generally expect is that the isotropic term would dominate. This actually happens in some systems like strontium iridate to the lowest order. But in these systems, in the Kitaev systems, this does not happen. The reason it does not happen is because if you consider, so sodium iridate is like this. So you have a layered system with iridate octahedra in one layer, so in different layers, and sodium atoms in between. So the iridate octahedra, the iridium atoms in any given layer are actually arranged in a hexagonal lattice. And between any two iridium atoms, you have symmetrically placed oxygen atoms on either side, like the picture shown over here. They are at 90 degrees ideally. They're on either side. And because of the contribution of these two, and so typically the Hopkin terms that we consider are super exchange terms. So they are via these ligand atoms. Not, I mean, you can also consider direct DT hopping, but to the most dominant contribution comes via the oxygen atoms. And this contribution vanishes because of the symmetric placement of oxygen atoms in the system. So the isotropic part vanishes ideally in the system. So when the isotropic part vanishes, then you have to get higher order contributions. So the higher order contribution also comes from different intermediate processes. And these in particular involve the Hund's coupling between the J effective equal to half and J effective equal to 3/2 movements on a given site. So those are the terms which give rise to anisotropic interactions in the system. So it essentially comes from the Hund's coupling between the J equal to half and J equal to 3/2 moments on a given site. More generally, if you have to look at the kind of magnetic interaction that you have in these systems, in the most general case, just on the basis of symmetries, then for a bond which has C2H symmetry, the kind of terms that you can get are, first of all, the Heisenberg term and the Kitaev term, but also more general anisotropic terms like bond-directional off-diagonal interactions, gamma and gamma prime interactions, where the small gamma here refers to the spin component perpendicular to the plane of the bond. So if you're on the XY plane, then this refers to the Z component. And beta and alpha refer to the other two orthogonal components. So essentially, the Heisenberg term comes from direct DT hopping between neighboring sites, between neighboring iridium atoms, for instance. The anisotropic part comes from the Hund's coupling. You can also to this add further neighbor Heisenberg interactions, which will come from significant longer range hopping terms. And essentially, if you're theoretically modeling these systems, you're looking at the magnetic interaction, you have to in general consider all of these terms. And they could vary in their strengths, but you have to consider all of them. And you have to find out which is the stronger interaction, for instance. So, okay, now with this background, I'll go on to talk about our work. So our work is on sodium iridate. Now, I was saying, sodium iridate is a layered compound, which consists of alternate layers of iridate, octahedra, and sodium atoms. This system is known experimentally also to have a strong bond direction interaction, but that's not all. It also has other competing interactions, because of which it has a magnetically ordered ground state. In particular, it has a zigzag ordered ground state, which is essentially a type of magnetic order you can have in every layer, which looks like this. And between different layers, you have antiferromagnetically ordered spins. In this system, the Curie-wise temperature is much higher compared to the ordering temperature. It's negative, so that shows as antiferromagnetic order. The fact that it's much larger than the ordering temperature shows that the system is highly frustrated because the ordering happens at a much lower temperature compared to the Curie-wise temperature. Different energy gaps here. The spin-orbit coupling is comparable, but it's bigger than the Mott gap. The crystal field splitting is big, of course. The Hund's coupling is comparable. So we have a number of competing energy scales in the system, as we saw earlier, and these play a very important role in the physics that results from it. The objective of our study essentially is to look at the high field magnetoresponse of this material, sodium iridate, and up to fields of 60 Tesla using specific techniques. This is very important because usually these high fields are not easily realizable, but when you can realize them, they can give rise to they can essentially reveal some interesting physics about the system. And also we model this behavior theoretically using the kind of effective models that I was describing before. We try to reproduce the behavior that you see in experiment from a theoretical calculation. We try to compare that with what you see just on a qualitative basis and try to see which are the features that you can reproduce theoretically. The motivation for this study, of course, is first of all to understand the nature of magnetic interactions in the system. How strong are different competing interactions. This also tells you a little bit about the geometry, the kind of bonding angles and so on. it can also tell you about possible exotic behavior at intermediate fields once the zigzag order is overcome in the system. So these are the motivations for this study. Okay, now let's talk about the experimental setup. So what is done experimentally here is, first of all, you prepare the sodium iridate single crystals. Then you characterize them using some typical measures like magnetization as a function of temperature at a fixed small field to make sure that you have the order at the right temperature and other sorts of behavior. The resistance temperature behavior. And these are just meant to ensure that you have the right behavior that you expect for sodium iridate. Then the high field, the measurements as a function of the field. The torque as a function of the field is basically measured in two parts. First of all, in steady fields, and secondly, in pulsed fields for higher. When you go to high field regime, then you measure it using pulsed field measurements. So essentially what is done is that you have a cantilever on which you mount the sample. So when you apply a field, the magnetization the magnetization of a sample essentially refers in reflection of the cantilever. This deflection is measured using some indirect means like capacitive or piezoresistive measures. And this deflection, which is calculated, is then used to calculate the torque signal. The torque that you measure is actually perpendicular to the direction of the field. That's why we call it the anisotropic magnetization, or the it's perpendicular to the direction of the field, which is the z direction in the lab frame. One thing to note here is there's an angle theta between the direction of the field. This is the direction of the field and the normal to the sample. This is an angle which is varied, and this is also an important part of the results I'll show you later. So this is varied by varying the direction of the field. Also, there's an azimuthal angle phi, which is basically the angle between the x-axis fixed to the cantilever frame and the a-axis of the crystal a-axis. So these two will repeatedly appear in our results. So you have three frames here, as you can see, and I'm going to talk more about this in the theoretical part of the work. Okay, so now the salient features of the experimental results. So this is the torque that I was talking about earlier, the anisotropic torque as a function of the applied field. The field goes up to 60 Tesla. So the one striking feature that you see over here is in the range 20 to 40 Tesla. You have this peak and dip features. These are very robust. They always appear, I mean, most of the time. And they also show a sort of variation as you vary the value of theta, which is the orientation of the field with respect to the normal to the sample. And it shows systematic variation. This has also been verified more systematically by looking at theta ODH as a function of field and theta. This blue region here shows the change in sign of theta ODH. That is what tells you the position of the peak and dip. So you see there's a systematic variation over here. This was sort of a key feature of the experimental results, this peak and dip feature and its variation as a function of angle. It's something which we felt could, if you could reproduce this theoretically from certain models, then it could tell you something distinctive about the system. Theoretically, the approach that we took essentially was that the idea was essentially to calculate the torque response of those different effective models that I talked about before and try to compare this with the experimental behavior. The essential program is as follows. So you start with a particular model which has different kinds of terms. You add to that a field term, which is a constant G factor for simplicity. Even though this is not realistic for these systems, but you do this the first level approximation. And this is in the lab frame. So you have to do a bunch of basis transformations to get this into the octahedral frame. So first you go from the lab frame to the cantilever frame, from there to the crystal frame. And also the octahedra themselves are actually tilted with respect to the honeycomb lattice. So they're tilted, actually the direction perpendicular to the octahedron is a 1-1-1 direction. So you have to perform a further angle rotation. So you perform a bunch of basis transformations to go from the lab frame to the octahedral frame. And then in the octahedral frame, now you can approximately solve for the ground state of the system using something called a modified Lanchas algorithm. And using that ground state, you then calculate the magnetization, and then you transform that back to the lab frame, and you compare that result with what you see in experiment. And this is not a quantitative comparison, it's just a qualitative comparison of the features that you see in experiment. So now the preliminary theoretical results. Okay, so first thing I have to say here is that just we basically distinguish our models primarily on the basis of the sign of the Kitaev interaction. And the reason we do this is because from ab initio calculations, it is known that the sign of the Kitaev interaction in the systems is supposed to be ferromagnetic. But very early on, there was a proposal that you can also reproduce the experimental features known for these systems if you instead consider an antiferromagnetic Kitaev and a ferromagnetic Heisenberg interaction within the nearest neighbor model. And you need less competing interactions to stabilize the same zigzag order ground state and similar, and also reproduce the different experimental features. And this was interesting for theorists because then you need a lot less work if you have a nearest neighbor model. And so this negative Kitaev-Heisenberg model, or Kitaev-Heisenberg with an antiferromagnetic Kitaev interaction, was quite popular for a while. And that is the reason we decided to sort of distinguish our models on the basis of the sign of the Kitaev interaction. Also, one thing we always do is that we make sure that you have the right zigzag ordered ground state by calculating structure factors as order parameters for the magnetic ground state. And that is something you, for that, and therefore, when you consider a particular model, the kind of competing terms that you can have to stabilize that kind of ground state will also be determined by the sign of the Kitaev interaction. So the first model that we consider is an antiferromagnetic Kitaev-Heisenberg model with a Kitaev term that is positive or antiferromagnetic. That is model A. The other two classes of models are models with a ferromagnetic or negative Kitaev interaction, where they have different types of competing terms. You can either have a further neighbor interaction or nearest neighbor anisotropic gamma and gamma prime terms. And note that we are actually trying to consider the simplest possible models over here. So in principle, you could consider all of these terms, but we don't want that. We want the simplest number of terms, the lowest possible number of terms that you can take and still reproduce the behavior of the system. That is the idea. So if you look at the behavior of model A, so this is the red curve over here. As you can see, we have only depicted up to 60 Tesla, but you don't see any features. It's a completely monotonous behavior. What happens is that when you go to higher fields, essentially this will eventually show a peak, of course, and then it will go down, and then anisotropic magnetization will go to 0 as you expect when the system is completely field polarized. But you don't have any features at low fields. On the other hand, if you look at the results for models B and C, which both have a negative Kitaev interaction, which are the blue and the green curves respectively, then in both of these cases, you actually do see these kind of peak and dip features at low fields. This is just one example. And of course, now we also verify this by looking at the antiferromagnetic Kitaev interaction, the interaction with the models with positive Kitaev interaction, but with different types of competing terms, while also making sure that you do have the right magnetic ground state. And in general, we find that in none of these cases, do you ever see any features? So it's not possible to get any features at low fields for these kind of models. On the other hand, if you look at ferromagnetic Kitaev models with the ferromagnetic Kitaev and antiferromagnetic Heisenberg interaction, then for these models, we have verified for a range of orientations of the field and thetas and phis basically, we have verified that you do see this robust peak and dip feature. I have to mention here that specifically for model B, which is the one with further neighbor Heisenberg interactions, you very robustly see this peak and dip feature, something which always appears. It seems like it's a feature which is tied to the properties of this model. And what's more, you don't necessarily need a zigzag ordered ground state. So you could also consider, you could also consider a model which has competing interactions such that you don't have a zigzag order. You can have a different type of magnetic ground state order, like a stripy order. This is not realized in actual materials, not known experimentally, but it can be realized theoretically. And what you find is that in such systems also you see a peak and dip. So it is tied somehow to the sign of the Kitaev and the Heisenberg interaction that you have, but it's not necessarily something which is specific to sodium iridate, for instance. So it's a feature of this model. And now the thing is that in these systems, you essentially have a zigzag ordered ground state, right? So the scale at which the zigzag order is overcome is roughly of the same order where you see the peak and dip feature. So we can assume that this is roughly the scale where the magnetic order is overcome in the system. And the scale of this is basically similar to the scale of the energy scale of the competing interactions, because they are the reason why you get this kind of behavior at all. So it's tied to the scale of the competing interactions. So once you've overcome this peak and dip feature, you can, once you are at field values which go beyond the peak and dip feature, you are essentially in a regime where the physics is entirely determined by the Kitaev term, which is the largest scale in any of these models. And so this is the regime where we expect that you can realize Kitaev physics, any features that can come from Kitaev physics. And of course, if you go to large enough fields, then this will be completely overcome and you'll see a field polarized behavior, and this will go to 0. But in the intermediate regime, we feel that this is a regime which is interesting because this is where you can realize the spin liquid behavior possibly. We have also looked at the d tau dh as a function of field and orientation theta, which is something we saw in experiment. It's not identical, but we do see a similar qualitative behavior. So this is once again here, the regime in which the blue regime where the sign changes is basically signifies the position of the peak and dip feature. So we see that the orientation, the behavior is not exactly similar to what you see in experiment, but it's kind of qualitatively similar. There's a bit of variation here. Now, like I was saying earlier, because the regime where once you overcome the peak and dip feature, you are in a regime where the Kitaev interaction can become very important. This is something which we have verified by looking at the spin-spin correlations in the system. So we have calculated the spin-spin correlations for like a range of sites on your 24-site cluster. And we have done this as a function of field, applied field. And we've tried to see, because for the Kitaev model, we already know that the nearest neighbor, the spin correlations are ultra short range. They basically go to 0 beyond the nearest neighbor. What we find is that in our system also, once you cross a field of roughly 35 Tesla or so, you actually start seeing behavior where the spin correlations are practically 0 beyond the nearest neighbor. That basically confirms your belief that the Kitaev interaction is the dominant interaction beyond the position of the peak and dip feature. So the peak and dip feature is actually tied to overcoming the zigzag order in the system. And once you're beyond that regime, you actually have a system where you can play with Kitaev physics. And what this also tells you, it indicates, of course, I mean, quantum spin liquids have features other than short-range spin correlations, but it indicates that this could be a regime where you might be able to tune the system to a field-induced spin liquid behavior. So one interesting thing that we noticed, this was a while back, but we noticed that, so now a more popular candidate for Kitaev spin liquid, for realizing Kitaev spin liquid behavior is actually alpha ruthenium trichloride. And this has been much more extensively studied. But in this system, for a long time, there was like a lot of discussion about a field-induced spin liquid behavior. What we found is that there was a paper in which there was some discussion of magnetic torque as a function of field. And there also, we notice this peak and dip features that you see in the magnetic torque as a function of field. And it happens at a scale which is close to the scale of the zigzag order, scale where the zigzag order is overcome in these systems, which is around 7-8 Tesla. And it also goes away as a function of temperature. When you tune the system to a temperature beyond around 7 Kelvin or so, this peak feature vanishes, which shows that it is tied to overcoming the zigzag order in the system. And this also tells us that there are perhaps underlying universalities between these classes of materials, and the kind of behavior that you see is known to be present in alpha ruthenium trichloride is perhaps also realizable in sodium iridate, but at higher fields. So in conclusion, we have studied the high field torque response of the Kitaev material sodium iridate up to a field of 60 Tesla using a cantilever method with pulse field measurements. And we have observed these robust peak and dip features at an intermediate field regime, which also show systematic variation as a function of the orientation of the field with respect to the normal to the sample. We try to theoretically model this behavior by doing exact diagonalization on a 24-side cluster with periodic boundary conditions for these effective spin models, which are of the extended Kitaev-Heisenberg nature. And we have tried to reproduce the behavior seen in experiment. And what we find is that the peak dip feature is reproduced only by those models which have a ferromagnetic Kitaev interaction and not by their antiferromagnetic Kitaev counterparts. And moreover, this behavior is something which seems to be tied to the sign of the Kitaev interaction, and it does not necessarily depend on the presence of zigzag order in the system. And we also find short-range spin correlations in the intermediate field regime, which indicates the possibility of spin liquid physics in this regime. So thank you, and I would like to take any questions at this point.
Thank you very much. So yeah, does anybody have a question?
Yeah, I'd like to ask a question. So I didn't understand what is the reason why there is this peak dip feature. Is that something that can be understood intuitively, or is it some numerics?
I think, yeah, so like I was saying, something has happened here, but okay. So intuitively, I think from the fact that the peak dip happens at a scale which is close to the zigzag ordering scale in the system, which is around 15 Kelvin, I think it's reasonable to say that this peak and dip is actually connected to the overcoming the zigzag order in the system. So when you apply a magnetic field, then at some point the magnetic order is overcome. And then you go to an intermediate field regime before the system is completely spin polarized, where the anisotropic magnetization will anyway go to 0. You have a regime where the Kitaev scale becomes the most important scale, because in these models, Kitaev scale is typically the most dominant, which reflects the behavior in the real system. So then that is the scale at which you can play with spin liquid physics coming from the Kitaev model. So what we believe is that the peak and dip feature is perhaps tied to the scale at which you have a phase transition from the magnetically ordered state to some other state, which could be a spin liquid phase, but we don't know like a lot. We haven't really analyzed this very well. One thing that we have looked at is the spin correlations, which we find decay rapidly beyond the scale of the peak and dip feature. So which is further indication that this is the scale at which it is tied to the scale of the competing interactions, basically.
Okay, but if you had like the opposite sign of the Kitaev interaction, then the peak dip feature would not be present, right?
Yeah, that is true. So if you have,
could you still have a spin liquid phase then with the opposite sign of the Kitaev interactions?
So, well, what we see for the opposite side of the Kitaev interaction is that at a certain large energy scale, there's a single peak, and that peak corresponds to overcoming the Kitaev, that peak roughly corresponds to the scale of the Kitaev interaction. So, before that, now for small fields, well, we don't, of course, the zigzag order will have to be overcome at some point, but I'm not, I mean, if this is the signature of a phase transition, then you don't really see that for the case of the antiferromagnetic Kitaev model. I do expect that even in that case, the zigzag order which is present. So the thing is, it's not clear that what we are basically saying from here, what you're trying to see here is essentially what is the right ground state, like what describes the physical behavior of the system. So it's not even clear that the antiferromagnetic Kitaev model is actually a physical description. In fact, the whole idea is to show that, to compare the two and show which one is more physical. And what we find is that the Kitaev model is the one which is more physical, because it makes sense that the zigzag order is overcome at some point, and then you see a behavior where the short and spin correlations dominate. And in the antiferromagnetic Kitaev model, you don't see that. That could mean that perhaps this is not a physical description of the system, because after all, this is a theoretical model. So
okay, I guess my final question was, we cannot say that because there is a peak deep feature, that's a spin liquid, right? We cannot make that claim.
No. So what we are essentially saying, is that the peak dip feature is perhaps connected to a transition from the zigzag ordered state to the spin liquid. So the spin liquid behavior has to be there because you have a model which has a large Kitaev interaction. We expect it to be there in some regime. But what we are saying is that the peak dip feature signals the transition from the state where it is magnetically ordered to a state where you have short-range spin correlations. So you have to basically go beyond the scale if you want to be able to see spin liquid physics at all. That's what we're predicting basically.
Okay. Thank you.
My turn, I think. Yes, I was just, well, of course, one of my questions was the same as Ian, so it's fine. My other question is, in fact, I'm just curious of the way you determine the parameters of your trial models, because I have the impression from what you presented that you just basically tried a few set of parameters and looked at which one fits the data best. But I was just wondering if you just, what kind of means did you use to determine these parameters?
Well, like I was saying, one thing that we make sure is that on all of these cases, you actually compare the order parameters. So what we do is, one thing, we don't have a lot of constraints, but we do look at the order parameters for the different magnetically ordered states and we compare them. And this is one example. So we make sure that you have the zigzag order in all of the cases, that is the dominant order compared to all the others. In fact, this is another thing that as you see it as a function of field, you find that while all of them tend to become small at large fields, you don't really see, I mean, of course, you might have some exotic order, I don't really know, but you don't really see any of the regular magnetic orders at high fields. That's another indication that you perhaps may not have a magnetic order. Like if it's a transition, it's not a transition to another magnetically ordered state. But yeah, this is one means that we use to make sure that you have the right magnetic ground state. But that's pretty much the only constraint. And beyond that, some of the parameters that I have considered are from known references. But yeah, a lot of them are parameters I play around with. So we have done this over an extensive set of parameters, and many of them are actually determined only by this constraint.
But I guess, given that you have the freedom to rotate the sample or the field, or I mean, you could do some kind of tomography, right? You could devise a way, I suppose, to determine all 9 parameters that you have in the Heisenberg, Jarzhensky-Moria, and Kitaev terms for nearest neighbor interactions if you wanted to, and you might be in the position to determine all these parameters from the data in some kind of overdetermined fashion, right? I mean, has that been tried or, I mean, developed in any way, you think?
So all of the parameters, well, actually mostly the objective has been to, first of all, reduce the number of parameters that you need. So, okay, one thing is that in these systems, it is known that you don't have Jarzhensky-Moria interaction because of the presence of inversion symmetry of the bonds. So that is 0. So you don't consider that. And also we only consider, we try to look at, I mean, we do have further neighbor Heisenberg interactions. For the most part, we want to minimize the number of parameters. So we look at models which are, which are already well established and known to describe the materials like sodium iridate. And we look at what are the minimum number of parameters you can consider. And it turns out that these are Heisenberg, Kitaev, gamma prime, and further neighbor Heisenberg. And among these, we further try to minimize. Like if you have Heisenberg Kitaev, then if the Kitaev is negative, then you need to have J2, J3. The thing is, if your Kitaev is negative and you have a nearest neighbor negative Kitaev-Heisenberg model, if you have a nearest neighbor Kitaev-Heisenberg model with negative Kitaev interaction, then you actually can't have zigzag order. You have stripy order. You can't have zigzag order unless you have some additional interaction like J2, J3 or gamma prime. So you have to, that is why you have to consider those in your models. But if you have positive Kitaev, then you don't even need those. You just have the nearest neighbor model to look at to get the zigzag order. So in this way, we have tried to minimize the number of parameters and look at what is the minimal model that can give you this peak and dip behavior. And what we find is that any ferromagnetic Kitaev model with an antiferromagnetic Heisenberg interaction generally gives you this behavior, but it's stabilized further if you also have J2 and J3 in the system. So, and if you have gamma prime, then you can get it, but frankly speaking, it's kind of incidental. Now you can get it over a very small range of orientations for the gamma prime model. But for the J2 and J3 model, which is model B, that is the model which always gives you the peak and dip, which is seen in the experiment. So we basically sort of, we believe that this is the model which best describes the system. So that is the kind of approach that we have taken with these constraints, of course.
Thank you.
All right, so if we don't have any more questions, thank you again, Sarbajaya, for this nice talk. And I think it's all for today. So thank you everyone for joining us today for this shorter session. And I don't think there will be a seminar next week, but we will get back to you on that.